Like the book in the Odyssey, we're going to go on a journey today. I'm going to show you the wonderful world of waves. And no, not the waves from the psychedelic people in the 60s, although I'll be showing it with guitar strings and such. I'm going to show you actual waves, tangible waves, the ones that you literally have on a string. I'm going to show you how to derive the wave equation from a standing wave like a guitar string. And then I'm going to do a problem where you have one string that has a certain density, and then you're going to connect it to another string that has another density and see what happens. We're mainly going to calculate the energy transfer between the two mediums. This is really important in impedance matching in circuits and all that. Let's get started. So what we have here is a little bit of string, and we've just drawn parallel lines at the ends of them. So this piece, ds, this piece, let's call it theta, all right? And then this angle, let's call it phi. So right now we have a little length of string and a couple angles in between. Now we're going to draw on our forces. Okay, but first, this is x plus dx. Then this is f plus x plus dx. And this is just this is just f of x. So these vectors here, so what we have here is now we have the sum of forces acting on this little piece of string, right? And it's straight now because we're looking at a little piece, but overall it has this curved shape to it. Now that we have that, we're going to apply Newton's second law. So then we do that, but in this problem, we only have acceleration in the y direction. So our string, our grand total string, and this is the ds, right? Well, I mean, it's not actually accurate. I'm just doing a rough drawing. But there's that. And so there's only gonna be an up and down acceleration in the y direction. So we can conclude that a y is equal to d2y, some function that describes this, over d. So this is saying that this is acceleration here. But this can't just be a straight d, it must be partial. Because we're going to have a function, y will be a function of x and t. So now that we've established that, let's continue on with f equals ma. So it's really the sum of forces is equal to ma, but the sum of forces, as we know from our diagram, is this minus this. And since they're not in line, we have to take there's this triangle that's created, and there's this angle phi. We want this, so we have to do it in terms of the others. So we have to put a sine phi right there, minus f of x sine theta. And since the forces are going to be the same because the string is the same density, it's now denoted as f, and we've distributed the f out. So that's what that's what I'm going to write now. So now we have and we're going to, instead of write m, we're going to write rho, the density, times dm, or dx, sorry, a little distance. Times the partial squared with y, partial x, or partial t squared. So another assumption we're going to make is assume that phi and theta are very small. So that means we can make some approximations as to what the sine of phi and the sine of theta are. Approximately. But this is also equal, or approximate, oh, yeah, this is also equal, this is equal to partial y x t partial x. Now, we can rewrite this. Now, we're getting to the bottom of our page here, but we're getting closer and closer. Now, a trick we like to do is take the derivative with respect to x, or the partial with respect to x. Because what that's going to do is going to take out this dx. So d over dx. And then the same thing over here. I know that's not how you write it, but that's just the way it came out. So f. So now that becomes a second order derivative, or partial derivative. And then what happens here is bye-bye. Those go away, and you're left with rho partial y partial t squared. Now we have this wonderful equation. And what we can do now, we can do a little bit of algebraic rearranging and a little substitution. And rho over f is equal to 1 over velocity squared. So now we have the equation. We have this, and this is the wave equation. This obeys sines and cosines. Its solutions are sums of sines and cosines. It's a beautiful equation. It shows up in all sorts of things. Actually, this equation is the Schrödinger wave equation, just in a different kind of form. The Schrödinger wave equation has a different function there, but it's the same form. All right, so here's our problem. What is the transmitted energy from one string, rho 1, to another string, rho 2, where rho 2 is greater than rho 1, and assume no energy loss at the junction. So as we can see right here, there's this wave going through, and there's this junction right here, and this is a thicker, denser string than this one. So the density of rho 2 is going to be greater than the density of rho 1. And we have a situation where there's going to be a transmitted wave, a incident wave, and a reflected wave back through rho 1. So I've denoted them by these three, and they all follow this sinusoidal thing by our wave equation. So what this is saying that at the junction here, the sums of the incident and reflected wave must be equal to the wave that is transmitted. Now, continuing on, we can write out those expressions and cancel a lot of cosines, as you can see. So we're really just going to get... This comes if you take the derivative of all of them. So there's also this... So when you do this, there's going to be a bunch of k's that come out because we're doing it with respect to x and not t. So these wave numbers come out. So the rate at which work is done is equal to the power, which is here, and that's equal to the vector f dot v. But we know that just because there's no forces acting in the x or z directions, so it's just this one component of that dot product. But we also know that f of y is equal to f sine theta, which we also proved in our wave equation that this is equivalent to tan theta, which is also equivalent to the partial of f of x, partial of f times partial y partial x. So then what we can do is we can say that f partial y partial x partial y this right here, so we just plug in the derivative of yt with respect to x and yt with respect to t and set x equal to 0 and multiply them all together, and what you'll get there. So this is the work or the energy done of flowing through the junction.